Right. So welcome to another session. This is an NPTEL course EE72 Principles of Signal Estimation for MIMO OFDM wireless communications. And in week 3 of the live discussion course, we will be discussing the Cramer-Rao lower bound. And this is a very fundamental result in wireless communications and signal estimation. And we will see why this is very important in especially estimation theory. So so far, we studied a signal model y is hx plus v, and we got the channel estimate in the previous discussion as x transpose y over x transpose x. And this estimate was a Gaussian random variable with mean h, meaning unbiasedness, and with variance sigma square over x transpose x. Right. Now, what is the Cramer bound or the Cramer-Rao lower bound, as many people say? So it is a lower bound on the variance of the estimate, right? So what we have been seeing that we transmitted a uniform or rather a deterministic constant over time, which was not varying with time, and we transmitted it over a noisy medium, right? So it can be additive noise or multiplicative noise through channel fading, and we observed some fluctuations right in the output, and these fluctuations were sampled as y1 and so on up to yn over n time durations. And what we saw that for a very simple case, the estimate comes out to be the sample mean, right? The estimate comes out to be the sample mean. And if so, by red, I have, if you see, this is the original estimate, and the blue curves represent my which we are trying to predict or which we are trying to estimate, right? And h hat is not equal to h, right? So what can be the closest value of h hat, right? How close can we go so that we can reach h? And that estimate is the Cramer-Rao lower bound. Okay, and this is a very fundamental result in fundamental bound in wireless communications. Another similar bound was the Shannon's limit on data rate, right, on channel capacity. And this is also a very significant and important bound, and it has not been breached yet by researchers. So this is a very fundamental bound, similar to the Shannon's limit, right? So we will be seeing its derivation. And so week 3 is essentially revolving around the Cramer-Rao bound, and then we will solve some numericals. Okay. So we have the likelihood, right? So this is termed as the likelihood. And what is this function? So for y is hx plus n, the likelihood is 1 by under root 2 pi sigma square to the power n e to the power minus 1 by 2 sigma square summation so y minus hx square. So this function, you should remember this function, right? This is the likelihood function. Okay. And what we are trying to do, we are trying to maximize the likelihood function to get the ML estimate, maximum likelihood estimate. Right? That is what we tried to compute. And in the previous week, we saw how the maximum likelihood estimator works. Now, the PDF of any so any PDF when integrated from -infinity to infinity, it will always give 1, right? So the area under any curve, and if it is a probabilistic curve, then it is 1. Right? So say for instance, you have a Gaussian PDF or you have an exponential PDF, right? So the PDFs will always converge, right? And such that the area under the curve is 1. It is unity. Okay. Similarly, when we have a impulse unit impulse, then it is a at say 0 and you have infinity. Right. So now if we differentiate, let me just write the steps as let me just number the steps. So if you have any doubt, you can just ask. So if we differentiate the first step with respect to h, we are differentiating on both the sides, right? So at the LHS left hand side as well as on the right hand side. So if we differentiate, so del by del h, and this is del by del h of 1, which is 0, right? So differentiation of a constant is 0. Now what the next step in step 3, what I'm going to do is we will be multiplying and dividing by the likelihood. Okay, so I divide and multiply by the likelihood, and I bring the differential inside. Okay, so we get step 3, and this is now equal to 0, right? Because del by del h of 1 is 0. Okay. In the fourth step, now if you carefully look at this expression, you will see that this is nothing but the differential of the logarithmic of likelihood, right? That is differential of log likelihood. Okay, and the second part is as it is, and 0 also stands as it is in step 4. Now in step 5, we multiply both LHS and RHS with H. So we multiply LHS with H and the differential of log likelihood into the likelihood dy is H times 0, which is again 0. So the RHS is still 0. Okay. Now, for an unbiased estimator, that is when the expectation of H hat is H itself. Now, how will you compute the expectation of H hat? So we will be differentiating H hat with the PDF of the likelihood. Okay, this is very important. So we use the PDF of the likelihood itself. Okay, to compute the PDF, and this is my definition of expectation of H hat. Which is very important to note that to find the expectation of H hat, we are using the PDF of the likelihood. Okay, we are using PDF of the likelihood. So now we differentiate LHS and RHS with respect to H. In this step, right? So it's step 6 and step 7. So in step 6, we are now differentiating the LHS and RHS with respect to H. So this is your equation 1. Let's keep it as it is. OK, we'll come to it later. After step 5 will come later. OK, so if we differentiate step 6 on LHS and RHS with respect to H, we see that h hat del by del h py given h dy, and this is del by del h of h itself, which is 1. Okay. And now we again multiply and divide LHS with p of y given h, which is the likelihood. And in step 8, we get that h hat times, if you see, we are dividing by the likelihood and multiplying with the likelihood in the LHS. So they both cancel out each other. So we are manipulating the math here. And this is again nothing but this is the differential of the log likelihood. And in step 9, I term this as equation 2, right? So above we got equation 1. This was equation 1 in step 5. And in step 9, we have got equation 2. Now, in step 10, we subtract equation 2 with equation 1, and we get, what do we get? So if you see, equation 2 is h hat, the differential of log likelihood into likelihood dy, right? And equation 1 was h times differential of log likelihood into likelihood dy, right? So there is h in one equation and h hat in the other equation, if you see carefully. So if we subtract, we get h hat minus h, right? And the differential is a common factor. The likelihood is a common factor. Dy is a common factor, and 1 minus 0 is 1, right? 1 minus 0 is 1. So now this h hat minus h is nothing but the estimate error, and this is the this is actually differentiation of the log likelihood, right? This is the differential of the log likelihood. So now if you look carefully, if we saw above that expectation of h hat is integral h hat p y given h dy, right? So we are differentiating over the likelihood PDF. Similarly, if you see this expression, let me name it as expression 3 in step 11. So if you see this very carefully, you have this py dy, right? You have this py dy term, right? And so this is essentially the expectation of this term h hat, that is h hat minus h into the differential of log likelihood, right? So we can write it as expectation of h hat minus h, that is the estimation error into differential of log likelihood. If you don't understand, you can you are feel free to ask at any step, right? So this is a very important to understand that we are using the same definition as expectation of the um, estimate, and we are using the likelihood PDF itself, right? Now let this h hat minus h, this be a random variable x, and the differential of log likelihood be a random variable y. Okay. Now there is a theorem which is called as the Cauchy-Schwarz inequality, which states that for any two random variables x and y, the individual product of their second that is x expectation of x square times expectation of y square is greater than equal to expectation square of xy. Okay, this is the Cauchy-Schwarz inequality. So we use this Cauchy-Schwarz inequality in this step 12 to get step 13. So what is happening is that we have this random variable x, which was the estimation error, and the random variable y was the differential of log likelihood. So now applying Cauchy-Schwarz inequality, we are breaking it up into as expectation of h hat minus h square and expectation of del by del h, that is a differential of log likelihood square. Okay, and this is greater than equal to this is my expectation square x times y. Right? In the Cauchy-Schwarz inequality, this is x times y. Okay, and this was equal to 1 square, which is equal to 1. Okay, this is equal to 1 square, which is equal to 1 itself. So what we can say is that expectation of this term, that is estimation square, which is let me just name it as x, and let me name this term as y. So we can say that x times y is greater than equal to 1, right? This is in step 13, and in step 14, what we can say is that x is greater than equal to 1 by y, right? So in step 13, we get a form x times y is greater than equal to 1. Okay. And in step 14, we can say that x is greater than equal to 1 by y. Okay, so expectation of error is greater than equal to the expectation of square of the differential of log likelihood. Okay, and this is the famous Cramer lower bound. So what is this? This is the estimate error variance. So what we can infer that this variance in error estimate has to be greater than equal to this term, right? That is, this term cannot be equal to 0. So ideally, in an ideal world, if my variance in error is 0, that means h hat is h, right? But this is not happening, right? So there will always be some error in our estimate, and we have to deal with it because this is a noisy medium. This is an uncertain medium. We don't have control over the noise, and so there will be some error in the estimate. But we know what is the uh, minimum error in the estimate which has to be there, provided it is a unbiased estimator. Okay, this is a very important. Provided the estimator is unbiased, right? So we took this assumption that the estimator was unbiased estimator, and hence for an unbiased estimator we can achieve this minimum variance. Okay, and this term, the denominator of this Cramer lower bound, is called as the Fisher information, I, and is represented as I of h. Okay, this is also very important terminology, so you should know this, that this is called as the Fisher information. Okay, so an estimator is unbiased, that is expectation of h hat is h, right? And if it achieves a variance equal to the Cramer lower bound, in such cases the estimator is termed to be a minimum variance unbiased estimator, MVUE. This is a very important class of estimators, right? And this is the best estimate which is possible over a given data sample. That is, you achieve a unbiased estimator, and the estimator also achieves a minimum variance. And so this is the best you can do. This is the best which you can do. So you can't get a better estimator than this. That is, the MVUE is the best case scenario. Okay, so it is unbiased as well as it is achieving the minimum estimator. Okay. Now let us consider the vector parameter estimation. So far, what did we assume? We assume that if you are transmitting over time duration, so you are transmitting a deterministic constant signal, right? So now we are going to relax this assumption and say that h itself is varying with time. Right? So h is varying with time. So the parameter which we want to estimate itself is time varying, and we will be seeing that how our estimate changes. Okay. So now my h is represented as a vector h1 to hm. So it should be noted that we have m parameters. Okay. So you can visualize it, or the scenario can be visualized as, say we have m transmit antennas and you have, say, only a single receiver antenna. Okay. So this is a practical scenario which we are considering, and the you have m transmit antennas, you have a single receiver antenna, and this channel between the uh, each transmitter, say transmitter I and receiver, is given as HI. Okay. This HI is the channel coefficient between transmit antenna I and the received antenna. So now what we are going to consider is the transmission of pilot vector xi of k. Now this is very interesting. So say we have this in the transmitter side. Say this is x1 of k. So remember that k is now my time index and I is my antenna index. Okay. Similarly, xm of k. Right. So this is how you are going to transmit the pilots. Okay. And at output, because you have a single receiver antenna, so we will be getting h1, that is the channel, into x1 of k plus h2 x2 of k, so on hm xm of k plus our additive noise, right? So this can be expressed as a vector of the parameters which you want to estimate, and so this is the parameter vector times m pilot symbols x1 to xm of k plus our pk, which is the additive noise, right? So remember that this is over one time instant, over single time instant. So over multiple time instants, so over n time instants, right? So where 1 k n, right? So k is my indexing the time, I is indexing my antenna, and we have m antennas. Okay. So at each time, so we will be receiving some y1, y2, so on. So we'll be receiving in general a yk, and we will be receiving x1 of k, x2 of k from x2, similarly xm of k, right, from xm, which is the emit antenna, right? So each of this column, the column, this is the column, right? So the column represents the symbols which are transmitted by antenna 1. Okay, so note this very carefully, the way in which the matrix is being written, because if we reverse the or if we transpose the matrix, then the calculations will change, right? So we need to follow matrix notation, right? So this is transmitted by antenna 1. This so this is transmitted by antenna 2. This is transmitted by antenna M over n durations. Okay. And this is H1, H2, and HM, and so on. Okay. So yeah. And we need to now estimate these parameters. And so earlier we were estimating a single parameter, and now we are estimating um, a multiple parameters or a vector of parameters, and so it is called vector parameter estimation. So I will be stopping here because these were the contents of week 3. And then in week 4, we will be solving this vector channel estimation, and it will give a very famous result, which is called the Moore-Penrose pseudo inverse. So this is also a very important result in mathematics, and this is very famous result, which is called the Moore-Penrose pseudo inverse. And we will be seeing this when we discuss next week. Okay. So any doubts? I will be going to the problem solving. No doubts? Okay. Right. So this is the week 3 previous year questions. And fine. So we are given a fading channel estimation problem. We are given a fading channel estimation problem, and our signal model is yk is hxk plus vk, and this is a complex channel coefficient. Okay, we are given a x vector, we are given some y vector. Okay, and vk is IID 0 mean circular symmetric complex Gaussian noise. We are given some sigma square minus 3 dB. So just remember again that sigma square is in dB, so you need to convert sigma square to watts. Right. So current question is not dealing with it, but still I'll just tell you. So 10 log 10 sigma square in watts is sigma square in dB. The sigma square in watts will be 10 to the power sigma square in dB divided by 10. Okay, this is the standard procedure which is followed. The errors in the real and imaginary parts are. So you might remember that the real part had some h hat minus h squared. Similarly, the imaginary part had some h hat minus h squared, right? And so were they independent? Yes, both these errors are independent to each other, and you should remember that independence and uncorrelatedness does not mean that the values are equal. Okay, this is very important. So say for instance, let this be R, let this be I. Okay, and since both are IID, so what does that mean? That both are having R and I are coming from the same PDF, right? Say Gaussian 0 sigma square by 2. Coming from the same PDF, so this does not imply that it does not imply that R is equal to I. This is very important. Okay, so coming from same PDF does not mean that the values are equal. So this was I think question 10 of week 2, current week 2, right, where doubt was asked in the group that is equal correct. So that is why I'm clarifying that if two values are coming from the same PDF, it does not mean that their values are same. Okay, it does not mean their values are same. So yes, they are uncorrelated. Coming back to the question, so they are independent, they are uncorrelated. They also have zero mean. Yes, as it is mentioned in question itself, that zero mean circular symmetric. So it is all of these. Okay. Question 2. So again, we have ik is hx plus v, which is our signal model, and complex channel coefficient. We need to. Okay. So it is given by radius of 1/8 for the real and imaginary parts. So I think by now you should be familiar how to solve this problem. So probability that h hat minus h is less than 1/8. So probability that minus 1/8 h hat minus h 1/8, and this is actually question 10 week 2 of previous year, right? So this is a build up question. Right? So if you want to see its previous part, you can just check the previous week's video. Okay, so and in that we had solved that the variance of the real part and variance of imaginary part, they are 1 over 128. This we had solved in the last class, and we'll be using this value here. Okay, so how do we solve this further? So we convert it into a unit Gaussian, and so for that we will divide by the standard deviation, which is root of variance. So minus 1/8, and if we divide by root 128, so it will go to numerator, and we have h hat minus h times root of uh, 1/128, and this is 1/8 times root 128. Okay, and you can see that root 128 is actually root of 64 times 2, which is 8 root 2. Okay, so what will happen is you will have minus root 2 h hat minus h over root 1/128 and root 2. So this is essentially q of minus root 2 minus q of root 2, which is 1 minus 2q of. Okay, straightforward. And this is note that this is for only real or imaginary. So for the complex number, what will happen is that it will get squared up. Okay, fine. So given a log likelihood, what is the value of this quantity? So how will we solve this? Okay, so I'll just give you a hint because this is a current year also. This question has come. So just remember this, what we solved, that expectation of h hat is defined as integration h hat p by given h dy, and this is equal to 1. Okay, we will be using this concept, and this is also a hint. Okay, so if you use this to expand it, so what will happen is integration minus infinity to infinity, and this entire term you can consider it as h hat. Okay, this entire term, I mean, this is analogous to. Okay, it is not equal to. Okay, so h times del by del h of log p y given h, and into p of y given h dy. Okay, so this is this part. Okay, this is this part, and this is my value whose expectation I had to take. Okay, and so this is the hint which I have given for this question. So you need to essentially simplify it further. Solve for the answer, and it is fairly straightforward, and you will get the answer directly. Okay. So another hint, if you require, is that see the derivation of CRLB. Okay, so in the derivation, just see how we have expanded this these terms, right? So we did many manipulations, right? We multiplied with uh, some h, or we on both sides, or we multiplied and divided with the likelihood. Okay, just think about it, right? What can be done? And this is just 2 steps from here, and you will get the answer. Okay. So right, so for this question, so just to remind you that CRLB is actually 1 over expectation del by del h, that is differential of the log of likelihood squared, right? This was my CRLB, and this term, the denominator, was I of h, which is my Fisher parameter. So in this case, what we have been asked that, so this term seems to be the square of this term, right? So this is the square of the Fisher parameter. Okay. Fine. Right. Question 5. This is a very good question. And again, I will not be solving it completely. I will be giving you sufficient hint so that you can solve it yourself, because this is a current year question. So we are given that yk is root k times h plus vk. Okay. And we know that vk is Gaussian zeros mean sigma square variance. Okay. So what will be yk? So yk minus root kh is equal to vk, right? Therefore, yk is distributed as Gaussian h times root k mean and sigma square variance, right? So this is a shifted mean, right? So I have been saying this from last 2 classes now, that y is a shifted mean of your additive noise, right? So this is the PDF of yk. So just see what has been asked in this question. So you have been asked differential of log of likelihood. Okay, just see what has been asked in this question. It's del by del h log p y given h. Right, this is what has been asked in the question. So this is y, right? This is y. So what is the first step? Find y given, find the likelihood, right? So we will first find out what is probability of y given h. Then we have to take its logarithm, and then we have to differentiate it further. Right? This is going to be our 3 steps which you have to do. So in the first step I will do. So what is probability of y given h? So this is 1 by under root 2 pi sigma square to the power n e to the power minus 1 by 2 sigma square summation yk minus h root k square. Okay, this is what we have. Now it is kind of homework to you. So what you have to do is you need to find the logarithm of this, right? Find out the log of it and then differentiate it with respect to h, right? So this is step 2 and step 3. This is for step 1. And if you do these 2 steps, you will get the answer. Okay, straightforward. Now again, we are given the same question as above, and we will be discussing how to solve this. Now what has been asked is the Fisher information for this parameter. Okay, what is Fisher information? Fisher information is I of h, which is the denominator of my Cramer bound, which is expectation of del H log of the likelihood, which is P of I given H and the square of it. Okay. So just a minute. So how will we solve this? So you need to take the expectation of del by del H log of what was my likelihood? 1 by under root 2 pi sigma square to the power n e to the power minus 1 by 2 sigma square summation yk minus root k h squared. Okay. So if you take the log of it, so this term does not have h, right? So you have to differentiate it further with respect to h. So this term does not actually make any sense, right? So just try to understand. So this will be expectation of del by del h of course you have a square also. Yeah, del h of and this will be minus 1 by 2 sigma square summation yk minus 2k h squared. Okay. And if you differentiate this term with respect to h, you have expectation of. So if you differentiate this term with respect to h, so you will be applying the chain rule or differentiation. So you will have minus 1 by 2 sigma square summation. So 2 times. So this 2 comes down, right? To the power 2, right? So 2 times summation yk minus root kh into minus of root k, right? This is what we have. So the 2 will cancel out with these 2. The negative signs will cancel out each other, right? If you are able to see. And this is squared. So the only hint I will we have solved it sufficiently. So just as a last step. So this will be 1 by sigma square. Rather it will become. So see, now we are going to bring the square inside. Okay. So this will become 1 by sigma to the power 4. Okay, this will be sigma to the power 4. And this shall be summation k. And this will be b square k. Okay. If you have any doubts, you can ask. Okay. So try to understand what we have done. So this y minus root k of h can be expressed as b square k. Okay. And now I believe this is very straightforward. And another hint if you want, so you have to use arithmetic progression. So there are some, standard expansion terms which is used in arithmetic progression AP, and you need to use that to solve this, right? And you will get the answer. Okay, this is a fairly straightforward from here. So okay, so the same problem continues, and we need to find the Cramer bound. So the previous part, we had to find the Fisher information. Okay, IH. So IH we computed in the previous question 6. Okay, and CRLB is 1 over IH. So you need to compute IH in the above question, and you need to inverse the fraction. You will be getting this CRL. Okay. Right. Okay. So we again have the same signal model. So root of H plus VK, and the Cramer bound of the parameter H is what? Okay, so this is what he has asked. So let me just do it. So what was our likelihood? So P of Y given H was 1 by under root 2 pi sigma square to the power n exponential minus 1 by 2 sigma square summation yk minus root k h, right, squared. So this was our likelihood. Okay, and if you take the log of this likelihood, so I am just taking the term which we require, right? So this is the second term which is having h. The first term is not having h, so it will be differentiated to 0 anyways. Right? So what we'll have is minus 1 by 2 sigma square summation yk minus root k h squared. And if you differentiate it, what we get is minus 1 by 2 sigma square 2 times summation y of k minus root k of h into minus root k if you apply the chain rule, and what we get is and if we equate it to 0, because you have to differentiate and equate it to 0, so what we get is that summation root k by k is equal to summation h into root k. This is what you get, and so h hat is summation root k pi of k divided by let me just check. We have done some error. Yeah, so if you multiply this root k with this root k, it is actually k times h. Okay, so this is an error. So this will be k times h. So here we actually get summation k. So this is summation of yk divided by summation of root k. And this is my h hat. Okay. So we need to compute the variance of this h hat, right? Which is so how do you compute the variance? So if you compute the variance, so variance of root of yk divided by summation of k, and this will be 1 by summation k because it is squared, right? When you take a constant out of doing some variance, you get 1 by summation k, and variance of yk. This will be, this is what this is n sigma square. Okay. Okay. So what is this? Is this equal to, greater to, or lesser to than the CRLB? So that is something which you have to check. So you need to compute the CRLB in question 6. Sorry, question 7. You need to compute the CRLB by computing the Fisher estimate, and then you need to check whether this estimate which you have got is equal, less, or greater than the CRLB, right? So question 9. So we have a multi-antenna channel estimation scenario. We have 4 pilot vectors, x1, x2, x3, x4. Okay. So the number of transmit antennas is what, right? So this is what they have asked. So what is number of transmit antennas? So see, we have 4 time signals, right? What they have said. So in time 1, 2, 3, 4, right? That is why you have n equal to 4. So here you have x of 1, x2, x3, and x4, right? What is x1? This is 2 minus 2. Okay. What is x2? This is 3, 2. What is x3? This is 2 minus 3. And x4 is 2, 2. Right. So see what is happening is that, so intuitively, if you see this problem in the transmitter end, it seems that you have 2 antennas, right? Say antenna 1 and antenna 2, right? And now say 2 minus 2 if x1 is being transmitted, right? Similarly, 3, 2 if x2 is being transmitted, or 2 minus 3, right? So now 2, 2. Right, so antenna 1 will transmit the uh, first values which have been given, and antenna 2 will be transmitting the second value. So this system will be having 2 antennas at the transmitter end. Okay. Okay. So the similar question as above, multi-antenna channel estimation, and what is the pilot matrix X? Right. So just see what we did here. Right. So this is what is my X matrix, right? It is being transmitted. So if you just write it in a matrix form, 2 minus 2, 3, 2, 2 minus 3, 2, 2. Okay. So this is at T1. This is at T2. And similarly, this is at T4. Okay. But here you have a trick, and the trick is that you have the same matrix and its transpose also is even, right? So which is the correct answer. So, so you should remember what we saw in the previous derivation. So y of 1, y of 2, so on, y of n, right? And what did we have? X I of k, right? This is what we were having, such that uh, uh, so at each row we had a time index, right? So at row we have the time index, and in column we have the antenna index. Okay, so if that is what we mean, so what will this be? So this will be x1 of k, where k is 1 and 2. No, sorry, k is 1 to 4. Okay, k is 1 to 4. Similarly, this will be x2 of k. Okay, so what will be the matrix? So see, what is the signal by antenna 1 at time 1, right? So this is what we have in 2 minus 2. This is at time 1. Okay, this is at time 1. Okay, so 2 minus 2. This is time 1. Okay, 3, 2. This is in time 2. 2 minus 3. This is time 3. 2, 2. And this is time 4. So this is what we have. So the answer will be D, right? So fine. Any questions? Any question? So if no questions, then I believe that is all for this class. And I'll just stop presenting. So any discussion do you want to have? Any doubt in previous class, you are free to ask. I'll stop the recording. Right, thanks.